Welcome everyone. Now finally we are ready to put everything together to do Q-learning. And Q-learning tells us at this state how much good stuff will happen if I do this. So let's take a look at how Q-learning works. First, let's recap what are important components of reinforcement learning. Well, some reinforcement learning agents have information about the transition model and the reward model. Some don't. So we want to actually learn those two objects. Then some work over policies and some work over value functions. And the value functions are the expected total rewards of the agent's policy. And now Q-learning is using a version of this value function where we have the immediate action in the state that we are. That is basically something that we can try out. And then we follow the policy. And so we use the quality function, the Q function, that's where the name Q-learning comes from, to actually learn which one is the best policy. Now, the Q function gives us the expected total rewards of taking a specific action in a given state and then following a particular policy afterwards. So what we're gonna use here is the Bellman equation, which gives the best policy's value for a given state, which is here signified by this maximum of that chooses the action A. So we choose the best action to get the highest expected rewards. And then we have the discounted expected future rewards. So this is, if you would know the reward model and the transition model, we could do this. However, we don't know that, so we need something different. But before we gonna see how to learn these, we're gonna reformulate this Bellman equation into a Q function that just allows to have the value being dependent on each action that we can take in a different state. So also the conditional expectation on the rewards, and the transition matrix is now action-wise and not only state-wise. So the equivalence of these two is given because this maximum of the quality function, if you choose the maximal quality function, this gives us the value function of the state. The state, the best policy value is nothing else than choosing the best Q function. By choosing the right action, we get the best Q function. And from this, we can also extract the policy, so which policy it actually is that gives us the best value. Now, we combine actually in Q-learning what we have seen before, namely the temporal difference evaluation, because this helps us to sample efficiently update our estimates of the Q values and also the value functions of the states under a policy. Now, here is again the example that we have seen before. So we have the estimate of the Q function for being in state S1 and choosing to go right to S2. And that's revised by just the signal that we get once we go to S2. We get here a reward of 0, but we get some future possible rewards of 100. We discount that by 0.9, and then that gives us a new estimate of our Q function, which is 81.5. Now, the Q-learning puts everything together that we have, or some of the stuff that we have seen before, by doing the following. So we repeat in each and every step that we take the following. So we select and execute an action A, then we observe the next state and the next reward, and we update the counts, we update the learning rate, and then we update our Q value just like we did it in the temporal difference update. So this is the TD target, so the immediate reward plus the discounted future reward, and we take actually the best one that we can get, and then we subtract our previous estimate from this, and the difference is going to be our signal that we get, and we the alpha says how much we want to incorporate of that signal into our new revised estimate of the Q function, and we do that repeatedly until convergence. So this is a model-free temporal difference update and a sample-based variant of value iteration. So this updating is nothing else than the value iteration, basically only based on samples. Now what we also have here is the problem that when we just stick to a policy, then we can exploit that, but it could be that the learned model is not the real model, and so we get suboptimal results, so we get stuck on a bad policy. So we need to learn also a little bit, and so taking random actions, that gives us a little bit of exploration, and so we can learn about what is the right model. But what if we only learn, then we never exploit? That would be also not giving us the maximum of the reward. So we need to balance these two objectives. Especially what is the use of learning a complete model if some parts of them are not even worth going to? And how can we balance this? That's basically answering how we select and execute this A, and how we choose the learning rate. And there are a couple of ways. One that we already know, that's epsilon greedy. And here with the probability of epsilon, we choose a random action, and otherwise we execute the best action that we have. So then we are greedy. So the A star is the best action. That's the argmax of this Q function, which is a function of the state action pair. Then we could also do Boltzmann exploration. That gives us a probability of an action. So this makes the discrete actions actually continuous, a probability between 0 and 1. And this works by raising to the exponential this Q function divided by tau, a temperature parameter. And this comes from biology or natural phenomena, where if you have higher temperature, then you have more noise and more randomness, and then you do more exploration. But if you have low temperature, then you're more greedy. And so we raise to the exponential this Q function to make it positive, scale it with the temperature, and then we divide it by this normalization to get something that is between 0 and 1, so the probability. So if we do, for example, epsilon greedy, here we again have these conditions on the convergence, which mean that the epsilon should be such that we learn, but we stop learning after a while. So first we explore a lot because we are just starting and we need to learn what the values could be. But then later, when we have visited more and more often some states, we need to reduce the learning. So we can optimize a policy by reinforcement learning when we don't even know anything about the transition probabilities and the reward functions. And model-free value-based learning can work by Monte Carlo learning, which is unbiased but needs a lot of data, or temporal difference learning, which is more popular because it has low variance and needs less data but is biased. The learning has the exploration-exploitation dilemma. And in practice, Q-learning looks like follows in our grid world example. So here, remember, we start in the lower left corner, and then we have, for example, this policy, where we go then to the terminal state plus 1, which is our goal, because here we get the highest reward. And we want to avoid this -1 terminal state where we get a really bad reward. And so on each step we have a cost of minus 0.04. And discounting is 1 here, so we have no discounting. And we want to learn about actually what are the values of each of the states, of each of the squares here that we see. And to do that, we can actually run this. And here, this is run with value iteration. After 1,000 iterations, we see we get the best value estimate is 0.71 for this lower left corner. And then the best action is to go up, up, right, right, right. And then we get to the terminal state, which has 1. Here we have no learning, but we have noise of 20%. So we slip. The transitions are not perfect. And so the question is, can we actually learn this? Or how does this look like in Q-learning? And Q-learning actually just takes the same values like here. And you see here the 0.71 is the value of the best action. So we have for each and every action we have a value here, but the value of the state is taking the best action of the best policy here. And so this, after 100 iterations, it looks like this. And this is also, again, without learning. So again, based on value iteration. Now we want to learn this. How can we do that? Here is an example with using epsilon greedy with epsilon 0.9. And to just show you how this looks in practice, I have here an example. And you can also see this in live action. Where we here can explore with 90% random choices what the values are of each and every state. So here you see there is a lot of exploration going on. And finally, if we run this until the end, this should look something like we have seen here. And now if we have less exploration, so only 10% exploration, we don't explore everything. So we get here some of the estimates. So the 0.95, for example, is the same here. They're also pretty close, but they're a little bit different. And we don't have good estimates for the values here down below. All right, here are some references, and let's summarize what we have seen. So how to learn taking actions in the specific states. Q-learning helps us do this, and it learns optimal actions without knowing the model. By balancing exploration and exploitation, we can actually achieve the optimal way to get estimates for each and every step and get the optimal policy. Epsilon greedy and Boltzmann exploration are commonly used methods, and we need sufficient exploration to guarantee convergence. Thanks for watching.